Hello and welcome. I'm Robert Graf, and today we're doing a special segment on acid-base regulation. And the reason why we're doing this is because we can integrate what we've learned in the respiratory system as well as in the kidney filtration system, and even bring in some of the nervous system since we've had all these units before. That's why I call this a special unit. And what we're going to do is I'm going to walk you through the slides to help you out with the assignment that I've given you, which is a critical thinking assignment, because we can do that now in physiology with this much information. And without further ado, I'll walk you through those slides and tell you what you need to know so that you can break up into your discussion groups and try this out with each other. So, pardon me while I get this going. Alright. So again, this is acid-base regulation. I think it's working. And the first thing I want to remind you of is that acid-base disturbances may be incompletely compensated. This is a part of homeostasis. And in the middle region there, you see the optimal operating range, the normal pH range, indicated about 7.4. And you can see this better in your notes or on your computer because you have this information. But this is the figure this is the first figure. And the important thing to remember from homeostasis is that if you go outside of the optimal range, we need to compensate. And we compensate in various ways. If we go too far to the left, it's acidosis, and we can use the respiratory system and the kidney system to immediately pull that back. If we go too far the other way, it's alkalosis. Same problem. So let's begin to get into that. And pH is going to be one of our more important units along the way. The next one is this one, pH balance in the body. In the upper part of this, you can see that hydrogen sort of goes through the body, and we get it in the input form of our diet, fatty acids and amino acids, and also through CO2. So we're bringing in the respiratory system as well as the digestive system. And then how we compensate for that is in the bottom with hydrogen ion output, which renally we're going to do through elimination with a little trick I'm going to show you with hydrogen ions that are put together in ammonium into the urea, where they can't go back, so they are eliminated, whereas we can do smaller compensatory changes with ventilation, and this is through carbon dioxide. We're going to see that we're going to measure the partial pressure of carbon dioxide. So let's keep going. This one, maybe you can't see it that well, but the idea is this is table 1610 out of your Fox book. Acidosis respiratory would involve the lungs. Acidosis metabolism is going to involve more the kidney. And you see that there's this sort of trade-off, that there's different ways that we can compensate for this. In the bottom part of this figure, this is going to help you for your handout work. Read this compensated acidosis and alkalosis part. So I'm calling your attention to that for the assignment. Moving on, pH homeostasis depends on buffers. So we're going to bring in bicarbonate, which we know is in the blood. So in addition to that, we have phosphate ions. Moderate changes in pH can be compensated for easily with the lungs. We're going to bring in the renal system, as I mentioned, but mostly during times when things are more exaggerated in the body. Ventilation can handle it 75% of the time, which is great. But when we really need to change it and change it permanently, we're going to rely more on the kidney to use this ammonia and phosphate buffer system. I'm going to show you. So an equation that brings this all together is the Henderson-Hasselbalch equation. And you see that we're going to be able to measure from arterial blood the pH. We have these units in here. I'm not going to ask you to derive this, but I do want you to see that the bicarbonate is in this equation, as is the PCO2. So you can get the units for the PCO2, and you can see that here. Over on the left, it's millimeters of mercury, and you can see ranges 35 to 45. And on the bicarbonate, you can see it's milli per liter, milli equivalents per liter. And you can see that on the low end we have 21, and over on the high end we have more than 26. So when you look at your equations, this will be very helpful. I want you to put high values into that, and I want you to put low values into that. So that will help you out with that part. And there are also more tables in the book that where you and it gives you a feeling for it. Plasma CO2 normal, low, high, plasma bicarbonate low, high. Go through these and get familiar with the changes. Use that Henderson-Hasselbalch equation so it's not just looking at tables and memorizing information, but seeing how it works. And when we get together again in groups, we're going to talk about that. Now I know we talked about the nervous system a while ago, but I want you to see that we have the respiratory center in the brain. It uses the carotids, it uses the arterioles, things that we studied from cardiovascular earlier, and peripheral chemoreceptors, as well as some sensors that are in the CSF too, in order to help you with your hyperventilation, for example. You know, it's going to measure that in your blood system and change things based upon that. So go back and take a look at these figures from earlier on, and I have provided you those. So here's more tables that I want you to walk yourself through. Maybe on the causes part, cover that up. Take a look at that situation and see if you can come up with that on your own. And in the end, it's a lot of systems. It's the nervous system, it's the respiratory system, it's the urinary system. But in the end, and it's a buffering system, but in all, you see that what it really is doing is managing the hydrogen ion input and output in the body. On a cellular basis, I want you to see that in the kidney, we're looking at how the bicarb is influenced and eliminated as a result of both pumps and using the chemical gradient of sodium as well. So you see that in the purple proteins that are in the proximal tubules and in the distal tubules. This will help you answer the questions as well. So here's our little summary that I put together for you. The blood pH can deviate from its homeostatic range. PCO2 is what metabolic receptors of the carotid artery measure, causes our metabolic acidosis and metabolic alkalosis. Concentratory reactions occur in the blood using buffers. Cells of the kidney and lungs can drive reactionary mechanisms to reinstate the homeostatic range. Lungs can decrease or increase PCO2. Kidneys can increase or decrease bicarb. And you saw the equation, the Henderson-Hasselbalch equation. That's the best way for you to get a feeling for this. A kidney, as we mentioned, can eliminate hydrogen buffered in ammonia or ammonium. So ammonia or ammonium. But that's ultimately through urea release to the outside. So that in a nutshell ought to get you going. And I just wanted to come back here for a second. I think you know your groups and you know where to take this from here. But if you have any questions, and I'll be around, I'm here to help you out on this. And I hope that you can integrate this information well. By the time you're done with it, in the beginning you may struggle a little bit, might have to go back and review a little bit, but overall I think it's a worthwhile activity, and I'm looking forward to working with you on it. So if there aren't any questions, then we can ask those questions while we're working on it. Thank you so much.